So, good morning, students. Today is July the 12th, and we're going to work on 3.4. We're going to talk about multiplication, okay? And the good news is I'm not going to do multiplication of other bases. Just let's stick to base 10. We're going to start with something very basic, and you know this, but we'll still go over it. How do you multiply these two numbers? 234 by, let's say, 12. How do we do that? Now, unfortunately, I'll do it by hand here. I'll just write down. If you're multiplying, so this is just the algorithm that you already know. And we're going to, of course, expand on it a little bit, okay? And I did assign you problems from 3.4. I don't believe most of you will have trouble. I think it's a fairly straightforward section. But if you do have trouble, you can always ask, and I'll be happy to help you. So the way we were taught, 4 times 2 is 8, 3 times 2 is 6, 2 times 2 is 4, and you can put a 0 or a cross sign, doesn't matter. 4 times 1 is 4, 3 times 1 is 3, 2 times 1 is 2, and you add them up correctly. 8, 4 plus 6 is 10, 4 plus 3 plus 1 is 8, and 2. Let me go ahead and quickly do a little check just to make sure I didn't mess up. 234 times 12. Yeah, we got it right. So that's fine. No big deal. We're going to look at different models of multiplication. How do we interpret multiplication? So here it's one of the things that your book talks about um, in the very first part of the section. It has a fancy name, and it's called Cartesian product. Some of it is in chapter 2 as well. I didn't cover it in chapter 2 because I knew we would do it here. So it's called Cartesian product. Let me bring the slide. Okay, it sounds like a fancy thing. Okay, let's see. You have two sets, A and B. Okay, set A has A elements, set B has B elements, and then A times B is defined as the Cartesian product of A and B. Well, what does that really mean? Let me give you an example. Okay, let me give you an example. Suppose A is this set, 1 comma 2, and B is this set, A comma B comma C. Okay, I want you to find A cross B. A cross B is a new set. The Cartesian product of A and B is defined as follows, guys. Okay, how many ways can I pair up somebody from A with somebody from B? The order matters here. Okay, A will be the first person, B will be the next. So I'm just going to start with A. Okay, so I'm going to put it like this. I can do 1 with A. I can do 1 with B. I can do 1 with C. I can then do the same thing, but this time with 2. Let me put this braces here. Give me 1 second. My computer is acting a little funny, but we'll address it. Don't worry. Unfortunately, it is acting funny. All right. So what's going on here? 1 with A, 1 with B, 1 with C. 2 with A, 2 with B, 2 with C. 2 with A, 2 with B, and 2 with C. These are the 6 cases I have. Now I'm supposed to put braces and the computer won't let me. I think I already have too many. So I'm going to put it by hand, and it's important that you put it there, okay? This is what we mean by A cross B, or the Cartesian product of A and B. This is how multiplication can be defined. This is another way multiplication can be defined. Now you're thinking, are you going to teach it in your to your fourth graders? No, you won't. It's something for you to understand where multiplication is coming from. That makes a lot of sense when you put it like this. Let me change the story a little bit. You are going to a pizza restaurant and you have two crusts, okay? I'm going to change the whole thing. Two crusts. One means thin crust. Two means deep dish. And you can get one of the three topping. You get to choose. A is pepperoni, B is onions, C is hamburger. Got it? Now you're asking, how many different pizzas can you get? The answer is six. Your thin crust with the three topping will give you three, and the deep dish with three toppings will give you another three, and you add them up, you get six. So it's kind of based on Cartesian product. Okay. So it's something that should work in the background when you study multiplication. Now, let me do a problem from your book. Let me walk you through a problem. It's a little hard to draw this picture. Let's go over it. What are they saying? The Cartesian product model, we have also, I mean, it's also in chapter 2, offers another way to discuss multiple. Suppose you order a burger on light or dark bread with one condiment, mustard, ketchup, horseradish. Okay, so you have burger. You can choose dark or light, whatever bread you want. And you get to choose, you have three choices for the condiments. You can either put ketchup, mustard, or horseradish. How many different burgers can you get? With dark, you're going to get dark with mustard, dark with ketchup, dark with horseradish. And your light bread can be paired up with the same three condiments. So you still have six choices. It's a visual representation of it's a visual representation of a Cartesian product. This is also called tree diagram because it looks like a tree. Okay, guys, let's see what else is coming up. All right, this is something we have kind of discussed, but we'll discuss it again. Okay, so 2 to the power third, I'm going to just give you an example instead of reading the slide. 2 to the power third is simply 2 times 2 times 2, which is really 8. That's how I write it. Now, this involves a couple of other nice formulas. For instance, by the way, this 2 is called the base, this 3 is called the power or the exponent. So what about this, guys? What about this? What about I want to write something like this? So I have the same base, but a different power this time. Let's say 4. Now, I'm going to expand it for you. Instead of 2 to the power 3, I can write 2 times 2 times 2. Instead of 2 to the power 4, I can write 2 times 2 times 2 times 2. Now, 2 to the power 3, and remember, there is a product symbol here, really. It's really a string of 7 twos. 2 times 2 times 2 times 2 times 2 times 2 times 2. I hope I have 7, 3, 3, 6, 7. I have 8. Let me make sure I have 7, 3, 3, 2. Yeah. So we can actually write 2 to the power 7. Now, look at this, guys. 2 to the power 3 times 2 to the power 4 is 2 to the power 7. What did we learn? We learned that they can be added. Well, I'm actually going to the next slide. So let me grab the next slide. I don't need this anymore. So this is what this is trying to say. When you have a whole number power, you can simply add. And this is the explanation why that works. Okay? So that's that. Let's see what else is coming up. Okay, another interesting one. Another interesting one that you want to understand is this one. Let's put it on top of this. And let's get rid of this. So what about this time you had another power? What do we do then? Let's say this time you have a power on top of this power. Well, according to the formula, you just multiply. But why? Let's make it 2 to keep things simple. Okay. Remember that by the definition of power, we can write this, right? 2 to the third raised to the power 2 means 2 to the third times 2 to the third. Now, 2 to the third is 2 times 2 times 2. And 2 to the third is 2 times 2 times 2. And that turns out to be 2 to the 6th. And that's why you can simply multiply the powers. You always don't want to go back and do it, break it down and do it. You can, it'll work, but it's something you should know that when you have two powers like that, a to the m raised to the power n, again, you can simply multiply the powers, and this time you don't add. Got it? Wonderful. Now let's do some problems. Okay, I'm going to do some problems. Now these are from your text, and I have assigned very similar problems from MATLAB, and I haven't assigned too many. There aren't too many good problems in this section. So let's do some of these. Show that 3/4, 3 times 4 is 12, using each of the following models. Okay, multiplication is repeated addition. What would repeated addition means? What would repeated addition mean? 3 times 4, 3 copies of 4. That simply means 4 plus 4 plus 4 plus 4, and we all know that is 12. This is what they mean by repeated addition. Instead of writing 3 times 4, you can write 4 plus 4 plus 4. What do they mean by rectangular array? Okay, we'll do that. A rectangular array simply means you have a rectangle that's 3 units by 4 units, or 4 units by 3 units, doesn't matter. Okay, now you're asking if you have a 3 by 4 rectangles, how many cells do you have? Let's count. 1, 2, 3. 1, 2, 3, that's 6. 1, 2, 3, that's 9. 1, 2, 3, that's 12. So here is what they mean by a rectangular model. This model shows you that 4 times 3 is 12. This is part B. Okay. Area model is very similar, guys. Area of a rectangle is given by length times width. Here you can say the length is, we just have to have unit squares. When you're talking about area model, you have to have all units have to be squares. So let me actually work on this for area model. So let's say these are all unit squares. Okay, now we didn't discuss area in this class, so I don't want to spend too much time. It's really like the array model, except for what's the area of a rectangle? Length times width. Let's say the length of the rectangle in this picture is 4 units. The width is 3. 3 times 4 is 12. That's the area model. That's what they mean by area model. Cartesian product. We just talked about Cartesian product, right, guys? So let's see. Let me erase all this because Cartesian product always takes some room. So you can do something like this. So let's say your sets are, A is 3 and B is 4. I'm gonna be a little patient and write the whole thing, okay? And B is 4 units. B, actually you can use 1, 2, 3, 4, but I'm gonna use A, B, C, D. No, no. The Cartesian product will be this. Again, I have to do braces first. Let me see. One with A, one with B, and it'll take some time. One with C, one with D. Okay. And I have to do the same thing with two, with three, with. All right. We have a big set. Unfortunately, I have to do it here because I need the room. Two, 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 three. All right, this is your Cartesian product. That's what they mean. I have to put braces here. Let me see if it'll take it. No, it won't. But I will do it here by hand. How many elements do you have in this set? You have 12. Okay, that's what they mean. Another way to look at it is this way. You have three choices for bread. You're at a pizza shop. One, two, three. Italian, white, brown. And that's for crust. Let's not go to the sub shop right now. Let's say we are in a pizza store and we have three choices for our bread crust. One, two, three. Let's say one is white, two is brown, and three is Italian. And you have four toppings: A, B, C, D, whatever they may be. How many different pizzas would you get? Could you possibly get? The answer is 12. So that's what they mean by Cartesian product. I hope that makes sense. And you can do these problems are fairly straightforward. I kind of did one. You can do two. There's nothing going on. Very similar to this, what we just did, right? Let me do two other problems from your book. Okay. Let me do two more problems. Okay, these problems are right here. Now I'm going to use tree diagram for this one. Suppose number 5, a sporting goods store has 6 shirts, 4 pairs of pants, and 3 vests. How many different outfits are possible? Now I'm going to show you one. Okay, then you're going to say, okay, that has to be 6 times. So shirt one, I'm going to call it S1, can be paired up with 4 pairs of pants. And what are they? I'm going to say P1, P2, and P3, and P4. Right? Then each pair can be paired up further with vest 1, vest 2, vest 3. Right? And you can see how tedious it gets really fast. Vest 1, vest 2, and vest 3. It's already getting very, very messy, isn't it? Very messy. So be a little patient. We'll see what we can do here. All right, delete this. So I'm going to meticulously draw this one out for you, just so that you can see that it's not so straightforward, okay? It takes a while. 1, 2. Okay, we're getting there. All right. So, so this can be paired up with this, this, and this. Once you choose your first pair of pants that has 3 branches for each vest, I know it doesn't look very pretty, but the idea is what counts. Now, you can copy paste it and do S2, S3, S4, S5, S6. I'm not going to do it. How many choices do I have for the first shot? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the answer will be 12 times 6. 12 times 6 is 72. Okay, so it's a tedious process. There's another way we can do it. It's called counting principle. Okay, so and that's more preferable. So you can say you have shirt. How many choices do you have for shirts? 6 for pants, 4, and for vests, 3. And you basically multiply. Okay, my picture on the right shows the case for shirt 1. You have to do it 5 more times. So it's 6 times 4 times 3. So what's the answer? The answer is 6 times 4 times 3 is equal to 12 times 60, 72, I believe, if I'm not mistaken. That's your answer. So I hope that helps. Let's try the other one. Okay, this one. Let me go take it to the next slide. I'm going to do the next one. Now, I'm not going to draw a tree diagram for this one, but what we are doing is really based on tree diagram. A new model of car is available in 4 exterior colors and 3 interior colors. Okay, so you can draw the tree diagram like I did. Um, that's fine. Or you can simply say each exterior color will be paired up with 3 interior colors. 4 of them will be paired up with 3 times 4, 12. So you could just do it like this. It's an alternate, and feel free to draw it. Exterior and interior. 4. Answer is 3 times 4 is 12. Got it? So that's all I have for you today. And what I want to do now, just briefly, I got some base 7 blocks. I'm going to kind of go back. That's all I have from 3.4, but I'm going to show you one example of addition and one example of subtraction from base 7, using base 7 blocks. Okay, guys? So kind of we're going back a little bit, just a little bit. Why am I doing it? Some students email me, they want to see more examples. So I'm just going to make up my example. I have a structure. I think maybe that'll help. So these are my base 7 blocks. This is 1, 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 49. 1, 2, 3, 4, 5, 6, 7. This is 7 to the power third. And what is 7 to the power third? I believe it's 343. 7 raised to the power 3. 343. So these are the base 7 blocks. Now we didn't do a lot of problems with base 7 blocks because I didn't have a good picture of base 7 blocks. Now that we do, let's do one. So let's say I want to add 1, 2, 6 in base 7, in base 7, 2, 2, this number in base 7. Let's do, I'm adding. All right. Now, of course, you can do it kind of the old-fashioned way. You can just say, I'm going to convert everything to base 10. I'm going to add them up. My answer will be in base 10. I'm going to convert it back to base 7, but that defeats the purpose, right? So I am going to do it the way I'm expected to do it. So what's going on here? Let's do it nicely. Now, unfortunately, I have to handwrite in the bottom, okay? I'll finally type it up. Don't worry. So guys, what's going on here? So I have 6 loose ones and 6 loose ones. I'll get 12 loose ones. From 12 loose ones, I'm gonna get rid of 12 is more than 7, right? I'm gonna have 5 here, 5 loose ones. I'm gonna take 7 of the loose ones and stick it to the next one, get a stick for it, stick it right here. 5, 6, 7, 8. I have 8 rods. Okay. I have in the second column, I have 8 of these. Okay. I don't like anything above 7. I'm going to write 1. Okay, I'm going to take 7 of the rods. I'm going to get one of these. Okay, 3, 4, 5. That's the answer. Now that's the explanation. That's the answer. Let me write it down nicely. And of course, I'm going to check the answer in case I messed up. It's a little hard to see. I know that. So guys, what I'm going to do, remember guys, in base 7, I can write 6 plus 2 times 7 plus 1 times 49. That's how I'm going to write it here in my calculator. I'm going to show you what this is, and what this is. Then I'm going to add the top 2 numbers and get the answer, and hopefully they will match. The first one is 1 times 49, which is 7 times 7. Good enough. Plus 2 times 7 plus 6. And that's that's 69. Let me take this guy. And on the second line, I have 3, 5, I get 168. And my answer is hopefully 69 plus 188 is what I got. Let's try it. 69 plus 188. Got it. We got it right. Now, having said that, let's do the same problem. Well, not the same problem. Let's subtract. Now, of course, I can make a different set of numbers, but what's the point? So I'm going to just put it like this. All right. This becomes now subtraction. Now, if you want me to show you another specific base, you email me. Okay. I'll make my solids and I have to make this. It'll take me some time. I can do it while I'm teaching, right? But if you want another base, any base of your choice, just tell me this is not my answer right now. So I'm going to change this a little bit, okay? Just to make it more fun. So I'm going to, instead of doing 1, 2, 6, I'm going to do 1, 2, 4. All right. Six minus 4. I have 6 loose ones. I take it. You know, guys, I'm going to change the question a little more because this is not interesting enough. I'm going to make this 1. Now that's more interesting, I believe. So 6 loose ones, 4 loose ones, I subtract, I get 2. Easy, right? Now, I have one rod, one of these. I can subtract two. So from here, I am going to bring, I have three of these, right? I have three of these right here. I'm going to take one of the slabs, okay? Break it down into 7 rods. I already have 1 rod. I'll have 8 rods. From 8 rods, if you subtract 2 rods, you're going to get 6 rods. And you already got one. There's only 2 left here. Now, from 2 of the slabs, if you subtract 1, you're going to get 1. I know it's a little hard, guys. I know I don't know what else to do. And I realize that it is a little difficult. And that's why I didn't spend too much time on multiplication and division in another base. But if you can master this, you learn something from this class. Now, let me go back, check my answer, okay? So this is 316. 316 is 160. 124 67 and 162 is something 93. And I hope 160 minus 67 is 93. I hope 160 minus 67 is 93. So we didn't mess up. I hope that helps, guys. That's all I have for today. Try the problems from this multiplication section. I believe it's 3.4. There aren't too many, and our exam is coming up. And we'll have a short session tomorrow. I'll record a short video on 3.5, I believe, and we will wrap up chapter 3. And next week, we will do integers. I don't think it's a very difficult section, slightly more difficult than what we did today. We'll do division and wrap up division next class. I'll see you next class. Take care, guys. Bye-bye.